Hi guys! So I think I did this one right where you're not going to have to look sideways. Apologize for that. So this is the last part of our lesson. This actually could have been back during our thermodynamics unit because if you notice, we are going to be working with delta H. And if you remember, delta H is a change in enthalpy. And if you also remember, we said delta H was a state function, meaning that it had more than one way to be calculated. And guess what? Here's another way to calculate it using what we call bond energies. So if you take a look at the first definition on there, it's bond dissociation energy, and that's the energy needed to actually break a bond. Every bond requires energy to be broken, even if it wants to be broken. It's always going to require energy to break a bond, just like it would always require energy to break a bone. You have to put energy in. So some examples, if you take a look at this molecule right here, the way I have it drawn is we're breaking this bond right here. So you see that the CH3s and the CH3 are separated. To do that took 346 kilojoules of energy. So notice that this one was a single bond. So notice the energy for a single bond between those two carbons. Now notice in this molecule we have a double bond. So to break that energy and make them two separate molecules took 610 kilojoules. So notice it took more energy to break a double bond. We said before in our lessons that a single bond is longer and weaker than a double bond. And then if you notice on this one we have a triple bond we're breaking, leaving those two alone now, and that triple bond took 835 kilojoules of energy. So less energy for single bonds to break a single bond than a triple bond. Now you don't have to memorize your bond energies or anything crazy like that. Those are going to be given to you, so don't think you have to memorize these numbers, but you should be able to use them when given. Also, we know if it takes 346 kilojoules of energy to break that bond, if you look down here at this equation, notice we're reforming. We've formed the single bond. Well, if we know how much energy it took to break that same single bond up here, we can figure out how much energy it's going to take, or how much energy is going to be released when it forms that single bond. And you notice the same value, but negative sign, because reverse reactions, we flip the sign for our delta H's, just like in Hess's law. Now you might be thinking, where do I get these information from, these energies from? And you can see on your paper there, you have a table of bond energies. The table works where you follow it over to find your bond energies. So for example, we were doing a carbon-carbon single bond. So if you find where carbon meets carbon, there's your carbon-carbon single bond. Maybe you wanted to find the energy to break a hydrogen-fluorine bond. You would find hydrogen, carry it over to fluorine, and voila, there it is. Now, if you had done hydrogen on this side and followed it down to fluorine, you'd get an empty spot. I don't know why they left all this empty. I think they should have just repeated the data, but they didn't. So if that ever happens, just flip which side you're looking on. So like, for example, a nitrogen-chlorine bond is 192 and kilojoules per mole of energy would be needed. Now, up this top diagram is for single bonds, okay? Then the table on the bottom is for multiple bonds. So if you wanted nitrogen-nitrogen single bond, you'd follow nitrogen to nitrogen. There's a single bond for nitrogen-nitrogen. But a nitrogen-to-nitrogen double bond is 418, and a nitrogen-nitrogen triple bond is 945. So we're going to use this table of energies to then look at problems and look at reactions that are occurring and figure out what their change in energy is going to be.